Hi everybody. We will now begin with the first of four lessons on term structure modeling, also known as fixed income modeling. That terminology comes from the time when coupon bonds were pretty much the only term structure instruments, and of course they have fixed income over their lifetime. We'll have an introductory lesson on the basic rates and instruments, then a lesson on short rate models, mostly focusing on one-factor models. Then we'll have two lessons on forward rate models. One on the so-called Heath-Jarrell-Morton framework, or HJM framework, which models the entire continuum of instantaneous forward rates at once. We'll have another lesson on the so-called log-normal market models, which model discrete interbank reference rates, usually called LIBOR rates. It's true that LIBOR is about to disappear, but there is not yet much consensus on alternative reference rates, and I expect that the underlying mathematics will not necessarily change that much. As already mentioned, the current lesson is concerned with the basic rates and instruments. We will also look at various approaches to modeling the term structure, as well as the relations. So let's get started. Our basic financial instrument will be the zero coupon bond, which we will denote as follows: P little t capital T. And this is the time t price of a security that will pay 1 unit of currency, here denoted as a dollar, at time capital T. Capital T is the maturity of the bond. We refer to such a bond as a T-bond. Throughout, we will completely ignore default risk, i.e. the risk that the principal will not be paid at maturity. Recall that a coupon bond can be decomposed into a portfolio of zero coupon bonds. Now, zero coupon bonds trade in the market for maturities of up to 1 year. For larger maturities, you have to use financial engineering to synthesize zero coupon bonds. And you can do this from coupon bonds, forward rate agreements, swaps, etc. In the US market, in fact, there are instruments called STRIPS, which stands for Separate Trading of Registered Interest and Principal Securities. And these decompose treasury bonds into coupons and principal, thereby creating a supply of zero coupon bonds. Now, unlike for stock prices, zero coupon bond prices are not usually modeled directly. Instead, we may use the following approaches: pricing kernel models, short rate models, whole yield curve models, and market models. I'll briefly discuss pricing kernel models here, but we will devote entire lessons to the other three approaches. A pricing kernel model posits a strictly positive semi-martingale Z as real-world pricing kernel. And this Z will be called a state price deflator if also Z0 is equal to 1. The price of a contingent claim X with maturity capital T is then defined to be as follows. The time little t price of a contingent claim capital X with maturity capital T is then defined as follows. The pricing kernel Z therefore incorporates both the readjustments of probabilities for risk-neutral valuation as well as discounting. Now recall that a zero coupon bond pays an amount of xt equal to 1 at time capital T, and thus the zero coupon bond prices at time little t are simply given as follows. If Z is also a super martingale, it then follows that this expectation here is less than or equal to Z little t, and therefore the quantity on the right is less than or equal to 1. This implies that the zero coupon bond price is always less than or equal to 1, or equivalently, that interest rates are automatically greater or equal to 0. Another approach is short rate modeling, and the short rate RT is simply an idealized quantity which represents the instantaneous riskless rate of interest at time t. A short rate model would posit some kind of dynamics for RT. For example, the first short rate model, the so-called Vasicek model, dating back to 1977, assumes that the short rate follows the following stochastic differential equation. With the short rate is associated a financial security, namely the riskless bank account, and it is defined as follows. A forward rate, RTT, is a rate which can be locked in at time little t for some future borrowing lending period at time capital T. Here there are two approaches that we will look at. The Heath-Jarrell-Morton models allow one to model the entire yield curve of idealized instantaneous forward rates, which we denote as follows. On the other hand, the log-normal LIBOR market models model observable interbank discretely compounded forward rates, denoted as follows. We'll have much more to say about these later on. Interest rate models are often categorized into equilibrium models and no arbitrage models. Equilibrium models derive dynamics from economic considerations, typically starting from a representative investor. The Cox, Ingersoll Ross, Vasicek and Merton models are examples of this, and we shall have a look at them later on. These models often have the nice property of being time homogeneous, but as they typically have a rather small number of parameters, they are usually unable to fit observed prices exactly. In other words, they are wrong straight away. No arbitrage models, on the other hand, attempt to fit a model exactly to observed prices and volatilities. They use the prices of zero-coupon bonds, caplets and swaptions and calibrate to those. Examples of those are the Ho-Lee and Hull-White models that we shall see later. However, some equilibrium models are not arbitrage-free and therefore cannot be in equilibrium, and some no arbitrage models permit negative interest rates and thus allow mattress arbitrage. The idea here is that if interest rates are negative, then you can borrow money from the bank, put it under your mattress, and then, at a later date, return less money than what you borrowed, thereby creating a riskless profit. Just a comment here. The problem with this is, of course, that there is no mattress security in the model. Just because a model is arbitrage-free does not mean that it is necessarily a good model, because it may not take into account certain possibilities that the market permits, but the model does not. Though we will mostly ignore equilibrium models, it may be useful to understand how they work. Basically, with each market agent is associated a non-negative rate of consumption process C, which may be stochastic, and whose lifetime expected utility is given by the following real-world expectation. Here the function U gives the utility of consumption, and delta is a discount rate, not necessarily equal to the riskless rate, which is influenced by how much an agent prefers consumption right now to consumption in the future. An agent with a lifetime expected utility of this particular form must then choose a consumption process C to maximize this function U of C. Now this optimality condition can then be shown to yield an equation for the price of an asset as follows. Let's briefly see where this equation comes from. Consider a market with, amongst others, one asset ST, and let C star be the optimal consumption rate for an agent with the lifetime expected utility of this particular form. The agent can increase her consumption over a future period, from T to T plus delta T say, by foregoing some consumption over the period from 0 to delta T and investing in S. For example, if she reduces her consumption rate by an amount epsilon S0 over delta T over the period from 0 to delta T, then she will be able to buy an additional epsilon many assets S. She can sell those assets at time T to yield an increase in consumption rate of epsilon st over delta T for the period from T to T plus delta T. Now outside the intervals from 0 to delta T and T to T plus delta T, the consumption rate remains the same. In other words, consumption is only affected over these two periods. Now with this new adjusted rate of consumption, the expected lifetime utility is given as follows. Over the period from 0 to delta T, we have reduced the rate of consumption. From delta T to T, the consumption rate remains the same. From T to T plus delta T, we increase the consumption. And from T plus delta T to capital T, the consumption rate remains unchanged. Now this is the lifetime expected utility of the adjusted rate of consumption, and because C star is optimal, this lifetime expected utility must be less than or equal to the lifetime expected utility of the optimal rate of consumption. Now if we split this integral here into the 4 time intervals that we have over here, namely from 0 to delta t to t, etc., then we see that 2 of these integrals are exactly the same, namely this integral here and this integral here. And thus the optimality condition yields the following equation. Suppose now that we divide by epsilon and we let epsilon go to 0. If we look at this quantity over here, for example, and we divide it through by epsilon st over delta t, we would get the derivative u prime c star s in the limit as epsilon goes to 0. Because we do not have the st over delta t, these come outside. And thus in the limit as epsilon goes to 0, this integral goes to this integral here with the derivative u prime of the utility function u. The same goes here, where now we have a negative sign. So by letting epsilon go to 0, we obtain the following inequality. Now we would like delta t to go to 0. Before we do that, first note that if capital F is an antiderivative of little f, then we have the following limit equal to this limit. This is just the derivative of capital F, which is little f. In particular, the limit on the left is equal to f of x, where we do not need to talk about any derivatives at all. So now let delta t go to 0 in this expression here. Then the limit of the first term is equal to minus s0 times the value of the integrand evaluated at 0. In other words, it's equal to minus s0 times u prime c0 star. Similarly, if we let delta t go to 0 in this expression here, then we obtain st times the integrand evaluated at t. In other words, st e to the minus delta t u prime c star t. And that must be less than or equal to 0, according to this inequality here. If we rearrange it, we obtain the following inequality. Now we obtained this by decreasing consumption over the period from 0 to delta t, using that to buy an asset, then selling the asset at time t, and using the proceeds of the sale to increase consumption over the period from t to t plus delta t. But we can also do this the other way around. We can also increase consumption over the period from 0 to delta t, which we can finance by shorting s. In that way, we can prove exactly the opposite inequality, and therefore we must have equality in this expression here. We therefore obtain the following expression, as we stated before, and more generally, for s less than or equal to t, we obtain the following expression. Here, as we've stated before, delta and u are subjective and may differ from investor to investor, but it is assumed here that there is a representative agent for the market. The existence of such a representative agent can actually be proved when the market is complete and investors are non-satiated, i.e. greedy, i.e. prefer more money to less, and risk-averse, in other words, if they have an increasing and concave utility function. In that case, the expression for the price of the asset that we derived on the previous slide will show that zt is equal to e to the minus delta t u prime c star t is a pricing kernel. Once we have a pricing kernel, that will imply zero coupon bond prices, and zero coupon bond prices will imply an interest rate. Let's now make explicit several assumptions about the bond market that we make throughout. We will work in a probability space, omega fp, equipped with a filtration that satisfies the usual conditions, and we will typically require that there is a frictionless market for T-bonds for every maturity T strictly greater than 0. This means that there are infinitely many securities, one for every value of capital T. We further assume that the bond price, PTT, is a continuous semi-martingale for each maturity T, and that P capital T is equal to 1. Thus, for each capital T, we have a security whose evolution will look something like this, and it will terminate at the value 1. This here shows the evolution of a 1-year bond. Another assumption that we make is that for every fixed little t, the map capital T goes to the zero coupon bond price at time little t, is P almost surely differentiable. In other words, Pt capital T is differentiable in the second variable capital T, so that this partial derivative here exists. In other words, the T-bond price is smooth as a function of the maturity capital T, although as we saw on the previous slide, it's typically of infinite variation and therefore non-differentiable in the variable little t. As we already mentioned, there is no default risk. We do not necessarily assume that PTT is less than or equal to 1 almost surely. In other words, we allow for negative rates in some of our models and therefore for mattress arbitrage. In actual fact, the bug of negative rates seen in, for example, Gaussian interest rate models has become a feature as interest rates became negative for long periods in Europe after the credit crisis.